The last speaker for the morning session is Valérie, and she will talk about the durability of building airtightness.
Okay, it's working fine. Okay, so I won't present myself again. I'm still working in Cerema, and again, this is my colleague Nolwenn Hurrell that has been preparing this presentation. But I have been working quite in tight collaboration with her on this subject. So I told you a few hours ago that now there is requirement on airtightness in every new building. But of course, as soon as we set up these requirements, the stakeholders say there is no point in putting requirements in airtightness because you measure it when the building is finished, but within 1 year or 2 years, then the airtightness, you have no idea what it has become. So why would bother at commissioning if it's changed over the years right after the commissioning? And indeed, the durability of building airtightness becomes very important as soon as you have a requirement on it in the regulation. Otherwise, it doesn't make sense. So we set up this national project, which was called Durabilitaire, to study really the evolution of building airtightness over years. We've made an extensive state-of-the-art of heavy studies that have been done on this field, and we published it in French and in English. And in English, it's published in the AIVC technical note here. Again, no, doesn't work. Again, you can download it on the AIVC website, and so you've got all the information that I will give you here that are in this technical notes. There. So first, we will start. There is two big kinds of study and a third one that is the implementation. We will start with field studies in real building. In fact, to study the durability, either you test in existing building, what is it at commissioning and what is it after a few years, or you try to test in laboratory the durability of the products themselves. So first, we will come with a review of field studies in real building. So we have studied 14 studies from 8 countries, and we have tried to sum up in the same graph. All the information given is in all those articles. All those studies are very different from one another. Some studies only 2 houses, while others go up to 41 houses, or 61 even in one study. The year of construction of building is very different from one another. They have different level of airtightness at the beginning. This is not the same kind of buildings that are studied every time. Sometimes it's concrete, sometimes it's wood. And the result also of the evolution of the air permeability is very different. So we have tried to summarize it in those kind of graph. So I will try to give you an overview of what we have in information in this graph. So at the bottom, this is the mean building age. Okay, so how old was he after the second test? Okay, here on the vertical level, you've got the mean change measured in the air permeability. So for example, if I point at this study, in average, the building were around 11 years old and have changed in average of plus 15%. Okay. Then you've got the level of the airtightness at the beginning. Was it a very in N50? Was it a very tight building that were studied here? Those are the green dots. Quite tight, yellow, not that tight, which is red. Okay, and in the gray one, they have studied everything, so we cannot choose a color for this one. And the size of the bubble represents the size of the sample. Okay, so the more buildings there were in the study, the more the bubble is big. And last information that you've got here, it's the difference between the study. So here at the bottom of the line, it means that in this study here, one of the building have improved the airtightness of 30%, and one of the building has reduced the airtightness of 155%, basically. Okay, so those are all the information you've got in this graph. I will guide you through. First of all, you see that all the bubbles are above the line. So that means that for every study, we see that the air permeability over time has increased. Okay. in almost all the study, apart from one in Germany on passive houses. Here in this study specifically, they have found no change after 25 years. Then, so we see that airtightness tends to deteriorate after completion, and the mean exchange rate is, well, positive for half study, and the average of mean change is 24%. So that means that in average, it increased of 24%, the air permeabilities over the years. We see also that for each study, as I was saying at the beginning, there are always houses that have improved and houses where the air tightness has deteriorate over the year, up to 580% for one of the studies. So that means multiplied by 6. So that is quite a lot. And for the improving, it has improved for a study of almost 40% in one case. So we need to explain that. Why in some cases it deteriorates, and why in some cases it's improving. What is very interesting also here is that you see that there is no correlation between the mean age of the building and the deterioration. So it means that even if you do your durability test after 2 years, you will find this 25% deterioration. So what does that mean? It means that it changed at the beginning and then tend to stabilize. So everything up seems to happen in the very 2 first years, actually. And this has been confirmed with buildings that are that have been studied regularly. For example, in this study here, do you see my mouse there? Yeah, this one. What we have done is that we have tested the building at commissioning, after 1 year, after 2 years, after 3 years. And we found a big difference between commissioning and after 1 year, but it remains stable after 2 years and 3 years. So the same building tested 4 times have shown a big difference after 1 year, but then no longer change in the following years. We see also that what's changed in the percentage. Okay, so you would have expected that a tighter building would have, in percentage, have more change over the year, because the same size of leak would impact more a tighter building than a non-tighter building. Okay, but we see that tight building at the beginning deteriorate less in absolute value than non-tight building. Okay, we have the same percentage of deterioration for the green bubble and the red bubble in average, more or less. Then we see also that we cannot correlate the deterioration with the material used. Sometimes wood is really, really good, basically when there is a good airtightness layer, and sometimes this is terrible. Okay, concrete can be also very good as in durability, and sometimes it can be bad. But so we haven't found any correlation between the construction materials and the evolution of the airtightness. Now, what can explain those change in time? The first things probably is the building natural movements, the settlement of the building over the first years. Okay, so in Europe we don't have that much earthquake, but still we settle the building settle over the year. The second thing is that when you hit the house for the first time, you have a natural shrinkage of all the mastics and so on that can induce some leakage when the airtightness is done right at the end with mastics. Other things, of course, is that when people get into the house, they want to put the furniture on the walls, they want to hang some things on the walls, so they just make holes everywhere in the building envelope to install themselves in the house. So this can also explain the decrease over the first years of the building. Then another thing that can explain the specific decrease, what we have observed is that the bigger the house, the higher the house, the more decrease we observed. So that tend to go in the sense of the settlement, because the higher the building, the more settlement movement you will have after the first year. It seems that air barrier made with the plasterboards deteriorates in average more than air barrier made with the polyethylene membrane. Again, this seems to be consistent with this question of settlements, because polyethylene membrane have much more flexibilities. but they can also strongly deteriorate, above all, if there is a timber frame that penetrates inside the house, and this can induce, deterioration. Another explanation is probably poor workmanship and unsuitable implementation conditions. And this is something we will study definitely, because with all mastics and all airtightness products, there is on it a temperature on which, and a temperature and humidity level on which you can use it. But during the construction, people do not care if it's -5 and it's a moment to implement it. They implement it even if it's -5, while the mastic cannot be used below 10 degrees, for example. Okay, so this is something that needs further implementation also. What could explain the improvement? The settlement can also explain part of the improvement, and also the installation of carpet and floor finished after the original test. Sometimes they test while all the floor has not yet finished, and maybe improving that may improve their tightness. And also the fact of just simply plugging in the electrical sockets, you can also improve a little bit the airtightness. Wood expansion with humidity is one of the explanation, and well, the impact of the user. Another thing that is important to take into account is what is due to durability and what is due to the uncertainty in the airtightness test. Of course, when we see this evolution, as we have in average plus 24%, everything cannot be put on the uncertainty of the airtightness test. But it's very important to make sure that what we are observing is the durability in this kind of study and not a problem of airtightness test uncertainty. So for example, in the study we have done in the durability project, we made sure we're using the same measurement device, the same operator, and we were taking picture of everything prepared in the building to do exactly the same year after year, and make sure that this was not the reason of the evolution we observed. Now, the second part of the study was dedicated to evaluate what has been done in terms of controlled environment in laboratory to test the desirability of product. So here we have, the problem is the product is under various kind of loads. There is the mechanical loads that will push and press and depress the air barrier. There is thermal and humidity load, and in some cases, weathering load, such as irradiation or weighting. So we need to find out what needs to be reproduced on the air barrier to evaluate its durability. So certain studies from 8 countries have been studied here in this paper, and the main conclusion was we need a standard to do this test, because those tests are not comparable between each other, actually, because they were doing totally different things on the air barrier. Another conclusion was it is not possible to reproduce in laboratory the equivalent, for example, of 50 years of aging. We cannot do that because we've got multiple products with multiple kind of plastics and so on, and they won't age the same way. So one product with one material, you can age it and say, okay, it's equivalent to 50 years, but an assembly of products, it's much, much more difficult. The other thing is we definitely need, if we are to set a protocol here, to test the airtightness of the assembly and not the ability in terms of shearing and peeling of the products. We find out that some adhesive were very, very resistant, so impossible to shear and to peel after a long time, but they became no longer airtight because very small paths of air were appearing after some years. Okay, while they were still very mechanically resistant. And in the other hand, some other adhesive were still sticking very airtight with the membrane. But if we were testing the peeling and the shearing, it was peeling quite easily, but at a big pressure that would not occur in the building. So this is very important to test the ability of the assembly to remain airtight and not the mechanical property of products. And then implementation conditions impact, as I told you, probably the reason why there is such a lot of difference between projects, what we assume now, is that it depends on how the air barrier has been implemented and what were the temperature, dust, and humidity conditions when the air barrier has been implemented. So there are studies showing that even when you are doing exactly the same thing, you still have difference in the end in terms of value of airtightness. And knowing that, also there is a study from the UK showing that for all those buildings that try to pass at the last time with mastic, they make the test, it's 065 instead of 060. So quick, they come with mastic and put mastic at the last minute to try to save it and be at 0.6. Those last minute corrections seems to be less durable than the initial implementation. So what have been done in this study, I will in those studies, the most interesting study that I wanted to talk to you about is this study in Sweden, where they have 3 manufacturers, okay, and they have tried to implement the products in ideal conditions, in dusty condition, and in cold and humid environment to see the impact of the implementation condition on the aging and on the initial airtightness. Then they have applied their own protocol for aging artificially the products, the force. So it's big. It's like, I think 3 meters per 3 meters. It's in Borås in Sweden. And what they found out was really funny. Well, funny, I don't know, but at least it was interesting for us, we thought. So there is 3 manufacturers, as I say, so 3 products. And they implement it. So when it's a plain line, it means that it's before aging. The dots are after aging, so to evaluate the durability. Green is ideal condition, no dustiness, perfect temperature, perfect humidity. Blue is cold and humid, and orange is dusty. Okay, so what we see here is that the result totally depends on the manufacturer. So for example, if we take manufacturer 1, whatever the condition when you implement the product, you got the same result of airtightness for the first test. However, you see that if you have implemented the product in cold or in dusty climate, you will have the airtightness that will deteriorate after years. Okay, after, well, artificial aging. So this is for manufacturer 1. For manufacturer 2, you see that it does not impact the durability. You see that the dot on the plain line are one over the other. So the implementation condition do not affect the durability, but it does affect the initial measurement. Okay, so that means that the building will be, if it's implemented in cold and humid climate, it will be less airtight from the beginning. And for manufacturer 3, which is a great mix of everything, so you see that the plain line are different, so it affects the initial state, and it also greatly affects the durability of the project. You see that if it has been implemented in cold and humid condition, then you've got, the airtightness tend to deteriorate very, 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 very quickly. And oops, and so that was the last slide, sorry. And so this is why in our new durability project, what we try to do is on real field case study, we measure the temperature and the humidity and the dustiness during the implementation of the airtightness. Okay, so we do not make any constraint. We have 15 houses in which during all the construction phase, we measure temperature, humidity, and dustiness. And we will check in the end if we see a correlation between houses that change and houses that do not change with the implementation conditions. And that was it. I'm missing a thank you for your attention slide. I'm sorry for that.
Thank you very much. Any questions to? Yeah. You have.
Thank you very much. I have experience to measure the airtightness of building through the year, 1 year.
Mm-hmm.
So in Japan, and in summertime in Japan, the relative humidity is higher, so airtightness become higher, and the winter very dry, airtightness and not good, loose.
Yeah.
So how do you have any information for depending on the humidity?
Yes, so indeed, we have studied seasonal variation of air tightness. In the first durability project, we gathered a lot of indeed information from Japan, from Sweden, from France also. We made some measurements about the seasonal variation. What we found out is that if your construction is a wood construction without plastic foil, well, without a layer, polyethylene barrier, then indeed it will change because the wood will expand and retract with the humidity. So we will see those seasonal variation. But if you've got a house, a concrete house, or a house in wood, but with the polyethylene barrier, then it has no impact. On all the measurements we have done, we have seen absolutely no difference between summer and winter. And also what we have not chicken, sorry, that's lunchtime. What we have checked was we have a huge database of 500,000 data in France. And we have plotted the average air tightness per month of measurement to see if we were seeing this tendency, because if there were a difference between air tightness between winter and summer, we should see this on the database. And it's perfectly flat. So on the way we built in France and in Europe in general, I would say this is not observed in new building.
Okay, thank you very much.
And the questions is not just limited to Valérie. You can also feel free to ask questions to all the presenters in the morning sections. So I have a question.
Great.
So would you recommend to have a standard or requirement to do the air tightness test for the building, say every a couple of years? As we can see the air tightness, there are some deterioration. Do you recommend?
I definitely recommend to do the test every year or so, probably, but this is quite impossible to impose it. I mean, already imposing the test at commissioning was a challenge. Imposing a test for every owner every XX year is, I think, almost impossible. But that would be great. And even when you sell a house, it would be good that the following owner be informed of the level of air tightness of the house that he will buy. That, yeah, maybe we'll come to that, but it still need a few years, I think.
Yeah, so in that case, maybe use some materials to overcome the deterioration of the air tightness.
Yeah, but we don't know what is the reason for the deterioration right now. We assume, following this study of the this Swedish study, we have great hope that we will explain a lot of things with implementation conditions, but we're not sure of that.
Yeah, another thing is not question, just I remember yesterday the conversation with the Tabachi, and I remember he mentioned in Japan, if you use the same approach to building to make the construction of the building, the air tightness is pretty much the similar. If you use the same approach, same material, and the air tightness is pretty much similar, so that's why you do not do the testing. Is that correct?
May not be what I mentioned. Sorry,
No.
I cannot see your point. Please repeat.
My point is, in Japan at this moment, no longer required to do the air tightness. If you use the similar construction method, similar material, and the air tightness wouldn't change too much.
I didn't say so.
Oh, sorry.
I didn't say so.
Yeah.
But even though there is no compulsory requirement for buildings in Japan, but I am sure air tightness is very important. And there must be guidelines for builders, especially builders for detached houses, to improve their air tightness of their product. I'm sure. But yeah, again, I'm very interested in the airtightness of non-residential building. And I have a question to Valérie, if it is acceptable. If it is very high-rise building, the building itself can move due to the wind pressure. And sometimes, such as in Japan, there is a earthquake sometimes. So I'm afraid that the airtightness of that kind of large building can change due to that kind of effect. But I don't have any information. So if you have any information or any guess you can have, could you please share with us?
Okay, I will go with a guess then, because I mean, or I will come back in 10 years, maybe we'll have this information, because high-rise building, we are already trying to measure it, and houses, we are able to test the durability, but the durability of high-rise, this is yet a subject, I think, for a few years. I think this is worse indeed in high-rise building, where there is settlement and more movement and so on, probably. But I have absolutely no value, no studies that I am aware of the durability of airtightness of high-rise building. This is, yeah, I mean, we have seen what works it was to measure a high-rise building. They don't want to do that within 2 years. Maybe they will do it again in 2 years with the Austrian tower to see if it has changed or not. That would be interesting. But yeah, there is no study I am aware of this. And the uncertainty of the measurement is such that it would be difficult to decide whether it's durability of uncertainty in measurements. And to study the durability, you need to have plenty of data, because as I showed at the beginning, if you just look at one building, maybe it will have improved, maybe, so just one building doesn't mean anything. What means something is a general average to evaluate if it will deteriorate more or less than other building. So make 100 tests of high-rise building, and then we will check.
Yeah. Thank you. Any other questions? No.
I forgot to mention that the 2-floor houses were deteriorating more than the 1-floor houses. So probably if you get to 20 floors houses, it would be even more, but this is extrapolating. Arnold has a question, I think.
Yeah.
Yeah, maybe rather an open question about which way to go to improve airtightness of non-residential buildings and increase testing there. In your previous presentation, you showed that although in residential buildings in many countries we see a large share of houses being tested, that's not the case for non-residential buildings. And I'm wondering why this is the case, because for instance in Belgium we have the same methodology for residential buildings and non-residential buildings. So the driver for having buildings tested is the energy performance regulations, in which the effect of infiltration is taken into account using a conservative default method. That's the same approach for residential and non-residential buildings. And this hasn't led to a large amount of tests for non-residential buildings. First of all, because the energy performance requirements are less severe at the moment. It's difficult to say because they're not entirely comparable. But that's one of my assumptions, that the current requirements don't show the need to test non-residential buildings.
This is one, and the other one is that the test will cost much more than for a residential building. So for a residential building in France, it's like 300 euro to test houses or something like that. For a non-residential building, you can multiply it by 10 or 20 probably, and depending on the size, of course. And then in this case, it may be less expensive just to add some insulation to pass the required levels and performing the test. A test, when it's cheap, it's easy to do it. When it's expensive, well, maybe it's better to take another option, and also much less companies are able to do it. So it's makes things much more complicated for the designer. That's my point. Yeah. So we need to improve the standards to ease the test in non-residential buildings. That's the first step.
I think it's a complicated issue to compare the cost effectiveness of testing on not large non-residential buildings compared to individual residential buildings. What would be the basis of that comparison when the amount of energy being used by the larger buildings is so much bigger? You need some sort of normalization method or some scaling rules to really make that conclusion. Do you have a comment on that?
Yeah, try to have a cost of the test per square meter of house of per square meter of building. I have well, it's not linear per square meter, because as soon as you need more than one blower de fan, or let's say 2 fans, it's become complicated to find a company that is able to do it, and it will charge it much more, actually. So there is this kind of gap at some point when you need more than 2 fans, the price increase much more per square meter of or per cubic meter of the building. But I don't have any figures to say how much. I just say that it's become complicated because there is a few companies that are able to do it.
Thank you. So there's no questions from online audience, and just again, it's not just a question or discussion to validate anything you like to ask. If there's no more question, I think we may finish the morning sections a little bit earlier. Yeah, and yeah. So we finished the morning session a little bit earlier, and let's have the lunch break. So we will resume after lunch at the local time 14:35.